I'm going to mostly grade the approach you take to solving something. If you don't get the answer, you will lose points, but not a lot, especially if you understand the method. So it's important. It's always, I wore the shirt that says show your work, so it's always important. The more work you show me, the more partial credit you could possibly get. Does that make sense? So getting the answer is great. It would be awesome. Please, I want the answer. But what's more important actually is, do you understand the process to even try to get the answer, right? That's why I'm going to weight that heavier. Okay, I like it. So even if you don't get the answer, show me everything you've tried. Okay. So last time we talked about 3 really of the most basic methods to try to solve a problem. And the most basic method is the way that all my algebra students try to do every problem, which is the guess and check, which this book calls guess and test, right? There's kind of like different levels to guess and check. I got a little outline to keep me straight. There's the first level is random guess and check. I mean, just totally random guess and check. So let me put up here a problem. I want to put the numbers 1 through 6 in these circles so that the sum along any side is 12, right? This is a kind of classic little problem. You guys understand it? So you can use the numbers 1 through 6 one time each, but I need the sum in all the sides to be 12. So random guess and check would just be completely without any thought. Just put 1, 4, 2, 5, just put stuff down and then go, okay, that didn't work. Then randomly, so obviously random guess and check very infrequently is a good way to do it. You guys with me? You guys with me? So there's the most basic level of guess and check is like truly just put numbers in, okay. No thought involved. Then the next level is called systematic. And this is where you actually kind of keep track of the implications of certain choices you made. So for example, I could try to put the smallest numbers in these circles here on the corners and just see what that leads to. Do you see what I'm saying? So instead of just blind, random, throw numbers wherever the hell, have a system to it. Let me take the smaller numbers and put them here. Will this ever work? Remember, I want them to add to 12, right? No. You can very quickly see there's no number here. If I put a 6 there, that's 9. That's not 12. It's nowhere near 12. Are you guys kind of with me? So what would that lead you to think to try next then? Instead of the smallest numbers in the corners, maybe you can try the bigger number. Yeah, and then you would. So that's systematic. It's sort of like, is there some aspect of all the possible solutions that I can kind of break it up a bit and try and be a little more, well, the name, have a system to it instead of just blind throwing numbers in there. You guys follow? Okay, and then the ultimate guess and check is inferential. So that would be something sort of like this, but it's sort of like, if I put a 1 here, what do these two have to add up to be? 11. Do you see what I mean? If I put it, is everybody with me? Because all of the sides are supposed to add to 12. That's what the problem says, correct? I want to put numbers down everywhere so that they all add to 12 each way. If I put a 1 there, these have to add to 11. No two numbers from 1 to 6 adds to be, well, 5 and 6 do. Yeah. But could you do it again here? No. No. So you couldn't do it enough, right? If you put a 2 here, then these have to add to be 10. You can do it with 4 and 6, but do you have 5 and 5? You only have 1 5. You guys gonna follow me? Okay, maybe. And so you pretty much get to a point where you're like, okay, the bigger ones have to be out here. Because the implication of choosing a smaller number leads to something I can't make happen. That's the systematic approach. So now can I make it work? How do I make this side equal 12? Well, I'll put here 3. 2. one. So that'll work, right? So it ends up being the smaller ones on the inside and the big ones on the outside. Now, I'll have a student say something, and I understand this. They'll say, how the hell is it gonna help me in my everyday life, Jeff? You're gonna get questions like that too, especially if you're teaching some of the older students and you're teaching them, I mean, if you're teaching like middle school, you're gonna be teaching pre-algebra, you're gonna be teaching, even when you're doing long division, so the student's gonna look at you and go, what kind of calculator, dude? I got my phone, it's got a calculator in it. The shit is this for? And I desperately need you to be better than, yeah, you're right, let's just use this. Because then they take my class in college and I'm like, what the hell's wrong with you? No, I'm sorry. You guys kind of with me? So even what I'm really careful about, you have a desire to be an elementary school teacher. You need to understand, if you want to do that, you have got to represent every topic you teach well, right? If you do not like math, you will be teaching it. You must come to grips with that. You do not want to pass that to your students. That might be what happened to you. You think back to some of your elementary school teachers, and normally for me, I've talked to several people I've tutored, and sometimes it's a early math teacher was not flexible. They were doing something creative, and it was different from the way the teacher said, and the teacher said that's wrong. When the teacher should have said, I see your thought process, that's right, but can you do it this way? I need to make sure you can do it this way because that's going to lead to something. Much different approach there instead of, no, do it the way I showed you. Oh, yeah, so it's wrong, so I don't know anything? Okay, so then you shut down. Okay, enough, I'm sorry. All right. I just really gotta understand, if you're gonna be an elementary teacher, you have a lot of responsibility on your shoulders. Have you ever had a teacher that it seemed like they didn't even like what they were talking about? Mm-hmm. Right. Didn't those classes suck, like major? Not even because they weren't, animated or whatever, but because it's like, if you don't even like it, why the hell would I even try to like it? Right? Okay, I'll stop. Okay. Does that kind of make sense? So the three possibilities, the least thought involved, a little more thought, and then this one's like, if I do this, what will happen? How does that inform how to improve my guess? Does that make sense? Okay. By the way, I do have a handout with some problems we'll go over here in a bit. When do I use this? When's a good time to use this? Guess and check. When's a bad time to use guess and check? All right, because, for example, this is going to lead to the general answer. If I'm trying to solve an equation, couldn't I just guess some answers for x and see if it works? What if the answer was 11.7829? What if that was the answer, 11.7829? How likely is it you're just going to randomly choose that to try? Not. So if the answer is 11.7289, that means the possible answers, stupid big amount of possible answers, correct? This problem, how many possible arrangements are there? Not that many. There's a finite number for damn sure, right? There's not that many possibilities. Guess and check makes sense. I'm not going to be guessing and checking for the rest of my days, right? You guys kind of follow? So one thing is, if there's a limited number of possibilities, guess and check might be a good way to do it. Blah, 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 blah. Oh, sometimes we'll do some of the strategies not to solve the problem, but to get a better feel for it. Just to see what the hell the problem is even trying to get at. So you guess a number and then you see what it does, just to get a better feel for what the hell the problem is doing. So sometimes guess and check is not a way to solve a problem, it's just a way to kind of like explore what happens when I put a 2 in this thing, right? You guys kind of with me? Okay. Blah, blah, blah. Obviously, if you already have a really good guess what the answer is, you're going to try it. So that's a good time to do guess and check. Blah, 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 blah. Okay. The rest of them are pretty straightforward. The next thing we talked about was drawing a picture. The most obvious time to draw a picture is if you have a geometric problem, right? If they said, Farmer Sam wants to have a rectangular garden. Okay, I'm going to draw a rectangle. I'm going to label it, drawing a rectangle is a good visual anchor, right? Blah, 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 blah. I like to joke with students that if the problem is the shirt was discounted, you don't draw a shirt. It's not going to help you. But if it's the triangle, okay, draw a triangle. It's going to help you. And then the last thing we did last time was using a variable. right? And that was the one we kind of ended with. We did the everybody's exciting, like representing all odd numbers. You remember that a little bit? Yeah. And of course, using a variable is really good. Here's a problem that you could use a variable for. You all know how to find the average of three numbers, correct?
Yeah.
Okay. So what if I told you that three numbers average to be, let's see, how do I want to set this up? Oh, let's do this. Let's say that you made an 81 on the first test, 72 on the next test, and then you're curious, what do I have to make on the last test? Did I put this in the warm-ups? No, that was a different class. Huh? Okay, different class. I just like this example. What do I have to make on the third test so I average an 80? Right? Do you guys all agree I'm definitely averaging below an 80 right now? Those are my two test scores. My test average is below an 80. But I want to know, what do I have to make here so I get an average of an 80? So one way you can do this is where algebra shines. If there's something I don't know, but if I knew it, I knew exactly what to do. You kind of pretend like you know it. That's the funny thing about algebra. I'm going to pretend like I know the third grade. What is the third grade? I don't know, so we call it, yeah. Now, if I have any three numbers, how do you average them? Add them. So now you just do everything as if that was a number. That is algebra. Algebra says, oh, you don't know something? Pretend like it's, you know it, X, and then do shit. And then once you're done doing shit, you can solve for X. You can actually see what that number has to be. Yeah, it will. Yeah, sorry. Divided by 3. Because there's three numbers, right? So how do you find the average? Add them all up, divided by how many there are. And of course, I already told you what I want that to be. I want the average to be 80, right? So algebra is, normally I know all of these and I calculate this. This is backwards. Algebra is all about doing stuff backwards. And you're like, yeah, I got that impression. No. But that's the power of it, is it can go back in time. And then of course you have to know how to solve this, right? So I mean, what's the worst part about that equation? If it just wasn't there, it'd be so much better. Division, right? How do I kill division by 3? Multiply by 3. That's the great thing about equations. If you identify what part of the equation you don't like, very often you can kill it. Or cancel it, if you don't like my violent math. Die. Okay. So over here I get
$240.
240. Right, 3 times 8, then add a 0. And over here I get, see, these are dead, right? Die. 153 plus x. And now, can you guys figure out what x is?
I'm sorry, how did you get to the 153? You divided by
81 plus 72.
Okay.
When I multiply by 3, these canceled. It is no longer
So you
there.
would start on the 80 side and then work your way towards?
So what I did, I multiplied both sides by 3. This side became 240. This side, the 3's canceled.
Like, why did the 3 get canceled with you?
Oh, all right, help me out. What's 12 divided by 3? 12 divided by 3. I know, I'm putting you on the spot, I'm
I
sorry.
know, that's pretty embarrassing. 4?
4.
Okay.
And what's 4 times 3? 12. So what's the shortcut? Division by 3, multiplication by 3 cancel each other out. They're opposite operations, so they're going to cancel. It's all like me saying, pick a number, now add 7, now subtract 7. Of course I got the same damn number I started with, right? You guys all with me? Okay. Sort of thing. So how do you get x by itself? What do you... Yeah, subtract 153, and what do you get? 87. So I need to make an 87 to lift my average to an 80.
Students got this. The students got this.
Maybe. Depends. Now, real quick, I want to show you a different way to solve this. Does anyone have a different way to solve this without using algebra? Yeah.
I know it's 80, so I can bring that 81 down to 80.
Oh, this kicks ass, exactly. So how far away from 80 is 81? 1 up. How far away from 80 is 72? 8 down. Overall, how far from 80 am I? 7 down. So this has got to make up for that. 7 up from 80 is 87. Done.
Yeah, that was great.
Oh, wow.
You with me?
Math's crazy.
I know. And I want to show you real quick. Can you give me 3 numbers that average to be 30? I'm sorry, 10. 3 numbers that average to be 10. The easiest 3 numbers that average to be 10 are 10, 10, 10. You agree? Why do they average to be 10? Because they add up to be 30. I kind of gave that away. So if I take this down by 1, doesn't one of these have to go up by 1? Don't they still add to 30? Isn't that still an average of 10? Isn't that basically what this process kind of uses? How far up or down? If you don't understand what I just did here, it's not the end of the world. It's okay. It's definitely a weird little thing. It's really cool. So if I took this down by 7, this has got to go up by. These still average to be 30. I'm sorry, average to be 10 because they add to be 30 still, right? That's all I'm doing here. How far away from 80? How far away from 80? So how far away from 80 does this have to be to make up for how down I am? So it's got to be 7 up. Same answer, sweet. Okay, that was all a bit of a side note, but it's still problem solving, yeah.
Can you do it in like reverse? Say you have like the 2, 10, 18. Can you use like your method to like figure out the average without doing the equation?
Sort of, yeah. You'd have to figure out, I mean, the worse the numbers get, the harder it is. This is relatively easy because these are symmetric. So if I take 8 from that, all of them are 10, so the average is 10.
Okay.
So if it's, do you see what I mean by symmetric? Like 10 is the middle, 18 and 2 are the out. So do they all have to, if I just gave you a group of 3 numbers, what's the number that you're going up and down? I don't know.
Yeah.
Yeah. So if you got a nice problem, of course there's easier ways to do it. Okay, everybody sort of with me? So that was another place you could use a variable, but in general, you don't have to. Algebra is one tool. When do you have to use algebra? When you're in algebra class. When you're not in algebra class, you could use it if you want to. Sometimes it's the best tool. Very often it's not, right? It just is. I'm gonna be honest with you. So of course when you're in algebra class, you gotta use algebra. Okay. We did, remind me guys, we did consecutive numbers last time, is that right? You guys remember that? Consecutive numbers? Yes, okay, good. There's some problems like that in the homework, for example, right? I'm trying to hit some like classic word problem kind of stuff. So today, what we're gonna focus on is in section 1, 2. So section 1, 1 was those 3. Draw a picture, use a variable, guess and check. Section 1, 2, incredibly enough, is another 3, right? And the first one of those is everybody's, now this is, I think, maybe some people's favorite. Look for a pattern. So they give you a classic problem for look for a pattern. It could just be directly like here, what is the next number in this sequence? That kind of problem, right? That's looking for a pattern, correct? Yeah. The pattern is I keep adding 3.
It'd be 10.
So it'd be 10. Yay. What about this one? Oh. Sorry.
Yeah, it's multiply negative 3.
I knew you. Obviously, he's not adding the same thing, right? So 2 main types of sequences are I keep adding or subtracting the same thing, or I keep dividing or multiplying the same thing, right? So you can very quickly see it's not adding the same thing or subtracting the same thing. But if I multiply by negative 3, each time, it works. So what's the next number?
Negative 162.
Yeah, negative 162. So you just multiply that by negative 3. So it's identifying a pattern and then using it, right? Yeah, we know so far. You guys have seen these kind of problems before. I have no idea how you feel about them, but here they are again. How many of you guys have seen this? I heard it is.
You have the previous two together.
Yeah,
The Fibonacci sequence.
good old Fibonacci.
How do you even like, because you guys are seeing that.
No, stop.
Yeah.
They have seen it before.
Yeah,
They have seen it before. You see what I'm saying? They didn't just figure it out. They've seen it before,
Yeah.
right? I know how you feel right now.
Yeah,
It's
yeah.
like me in painting class going, what? Right? They've just seen it before. They didn't just sit there and figure it out right now. So unfortunately, somebody already said the pattern, but that's okay. 1 + 1 is 2. 1 + 2 is 3. 2 + 3 is 5. Somebody help me out. You guys should all know this because you have these crazy people that let you do note cards on these little postcards. What do you call them? Note cards.
Yeah.
What's the size of one of these note cards? Isn't there 3 by 5? Right? 3 by
So many.
3 by 5, right?
Yeah.
So
Golden ratio.
a lot of, so for example, I'm only going to talk about this a little bit because you can have an entire freaking lifetime studying this insane sequence. The sequence seems really simple once you see the sequence. You're just playing with numbers, good job. But it models nature. It's insane. It's insane. Frequencies that sound good to our ear, harmonies that sound good to our ear are use frequencies from numbers that are in this sequence. Your alarm, if you have an alarm that goes that uses frequencies that are not in this sequence. So it has a lot to do with what we find aesthetically pleasing. Paintings that we like, they have certain things happening at certain positions that are coming from this sequence. And so it's not like, I had students say, well, is math controlling us? No, math is descriptive. It's just a description. So why would this be pleasing? Because it follows nature. What does nature do? As a snail grows, it builds its shell. Doesn't it build on itself?
Yeah.
Isn't that what this sequence is doing? So it's kind of like, of course this is going to sort of model. So like trees, if their branches haven't been cut, very many of them, as you go up, you'll see one branch, and then you'll see 2 branches, and then you'll go up a little further, and now there's 3 branches as you go up. So now there's like 1, 2, 3. If you look across, you kind of follow it. So if you look across, they'll bifurcate, they'll split, and they'll kind of follow this pattern. Pine cones, if you count the seeds, and all this stuff. So you could study the hell out of this. It's crazy. A friend of mine used Fibonacci sequence to make money in the stock market during the recession back in 2008, whatever.
Did it work?
Yeah, totally. It works.
I've heard of that,
Yeah, dude. So you could basically go to Google or Bing. Does anyone Bing? Good. All right, you shouldn't Bing, kids. Don't Bing. It's bad. Go to Google and just type in Fibonacci, whatever the shit you like. Fibonacci skateboard. I had a student come back to me and say, I found this skateboard that was designed in Fibonacci sequence. It's supposed to do this stuff. I had no idea. Fibonacci music. Yep. Fibonacci. Sorry. You'll find some stupid shit, but you'll find some really cool shit too. Yeah, there's a lot, like I said, there's a lot of stuff. There's golden ratio. I did some research into, oh God, don't bore the hell out of people. So there's something about the golden rectangle, and that has to do with what I said. The ratios of these things come from this Fibonacci sequence. And then you can go to higher level like polygons.
Yeah.
And that's a higher level thing. We're not going to do any of that, I'm sorry. Okay. So that's just another example of a type of sequence. It's not one of your classic sequences, addition and multiplication, but it's a more general sequence. Okay. Here's something that you wouldn't identify as being a sequence problem. Finding a pattern. I want to know, have you ever seen the right? No. What is what's the digit that's in the ones place of this number? Does everybody understand what this number is? Could you do this in your calculator? Try it. If you have a calculator, try to do this. So it's 3 to the. Call me over if you don't know where your to the button is. You should either have a caret or you should have a X to the Y button or something like that, or Y to the X button, right? For your to the.
I don't like this number.
Let everybody catch up. You're gonna get something weird. Do y'all agree that's gonna be stupid big? That is 3 times 3 times 3 times 3 times 3, 99 freaking threes. That's gonna be big. In fact, your calculator's not gonna know what to do with it. It's gonna give you something weird. Did you get a number?
I can't find the caret thing on the,
Oh, you got your,
yeah.
you do have it turned sideways, so
It's
you
like,
should have
it's
more
like,
stuff.
I think it's like X to the
It's a privacy.
Oh, here it is. Does this say X to the 1?
Next to the white.
Yeah, so you put 3, hit that button, 99. There's your caret.
Got it.
Hit 3,
under clear.
yeah.
It's
caret.
1.7.
Caret, it's right there. 2 the,
E47. Did you get an E47?
just this button right here, the 2 the, right here.
Too late to
Yeah,
start
yeah.
this in engineering mode to get the real
Sorry,
number.
I keep saying 2 the because
You're good.
that, I translate that to the word, to the phrase 2 the.
Yeah.
I see it, I don't even think about it.
So that XY button is the two that one.
Yeah.
Oh, no natural one. You have to hit the second, so hit 3, and then second that, I think. No, that's your E to the. Your to the button should, oh, there's your caret. So do 3, up arrow, 9, D9. Alright, how's everybody else doing? You alright? Okay. What do you get? 1 point,
7.7925069
E47.
Mine says times 10.
Good.
Times 47.
Instead of E, you say times 10 to the 47?
Okay.
But you have all the same digits here, right? Yeah. All the same numbers?
So
Okay.
it would be this number to the 47th power?
No. And does anybody else have these digits, but there's something else here?
Yes.
Some of you guys don't even have, it just says 47 at the end maybe or something, I don't know, like up a little bit. So what this means, do you guys remember scientific notation? All this means is, if this is positive and you move the decimal that way, 47 times. That's a big ass number, yes? So you literally multiply this by 10 47 times. So every time you multiply by 10, you move the decimal one, so I'm gonna move the decimal 47 times. Can't you see the last digit on your screen then? You cannot. Does everybody understand that? This number's big. This number's big, and your calculator is just like, okay, I'll show you that much. You know, because it's a poor little dude. It's got a little tiny screen. Right? It can't say continued on next calculator, and you go to your friend, oh, there's the rest of it, and then you guys kind of follow? So then you're like, okay, how the shit do I do this then, Jeff? My calculator can't do it. Well, we're humans, we're better than calculators. The hint I gave you is this is a look for a pattern problem. What is 3 to the first power? Holy shit. What's 3 squared? 9. What's 3 cubed? 27. 3 to the fourth power. You got calculators, you can use those too if you want to. 81. 3 to the fifth power. 243. All right, 3 to the sixth power. 729. I like it. Have you seen enough to see a pattern? Do you see a pattern? What's the pattern?
Each root is multiplying by 3.
That's how we get the numbers. What's the patterns? And this whole problem was about the last digit, correct? What's the last digit doing? 3, 9, 7, 1. 3, 9, I'll bet you a 7. Well, let's do it. What's 3 to the 7th? Just multiply that by 3.
2817.
2817.
Yeah.
So here's 1, 2, 3, 4. Every fourth one, it then starts over, right? Every fourth, so if I start, well, it's 1, 2, 3, it starts over. Are you guys kind of with me?
Oh.
Semi with me? Okay. So there's a problem like this in the homework. So 3 to the fifth power ends in 3, correct? So let me go back. What's 3 to the 0th power? Do you guys remember? What's it? Good, 1. So there we got 1397, 1397. See that? We can make this even better. Every fourth one, the last digit will be a 1. Every fourth power, the last digit will be a 1. That's the pattern we see. Do you see that? So 3 to the 8th is going to end in 1. 3 to the 44th is going to end in 1. You guys all with me so far? I really want this. But then it's just 1397. Now, I want you really. So if I have 3 to the 15th power, four goes into 12, not 15, right? Stay with me. Every 4 it starts over. Yeah? So how many's left over if I divide this by 4? 3. So 1, 2, 3. That's going to end in a 9. So 3 to the 15th power. Sorry, yeah, what did I do? 1, 2, 3, there it is. 1, 2, 3, it's going to end in a 7. Yeah, so all the remainder is going to tell you where you are in the pattern. Now let's start it up here. So 1, 2, 3, it's going to end in a 7. So if you divide the power by 4, because it repeats every 4th one, the remainder you get tells you where you are. So if it goes in evenly, you're starting at 1. It's going to end in 1. If it goes in with 1 remainder, it's going to end in 3. So what is 99 divided by 4? What's the remainder? Yeah, the remainder's 3. So therefore, this will end in a 1, 2, 3. It'll end in a 7. So every 4th power, it starts over again, correct? You with me? Does everybody see that? 1397, 1397. So every 4th power, it starts over again at 1. Yeah.
3 to the 7th, what's that number again?
3 to the 7th is 2817? 2187.
Go ahead.
So watch this. 3 to the 5th power. 4 goes into 5 how many times? 1. With how many left over? 1. So I should be at the first step. It should end in a 3, and it does. So whatever the power, if I did 3 to the 402nd power, 4 goes into that, how many's left? What's the remainder if I divide that by 4? So I'm going to be at this step, it's going to end in a 9. Can I check it in my calculator? No, that's the whole point. Yeah.
Can we just find what one the power is divisible by, and then it would end in that, like whatever that power ends in? That's kind of what it seems like it's working.
No, that's not at all what's working. So,
Like how 15, like that power is divisible by 3 to the 3rd power, so it's gonna end in the 7.
all right, so 3 to the,
Or, sorry,
3 to the 21st, 3 to the 21st.
Mhm.
That's divisible by 3, correct?
Yeah.
But that's not the right answer. 3 goes, 21 divided by 4, how many's left over? If you divide 21 by 4, how many's left over? No. How many's left over? 4 doesn't go into 21, it goes into 20. So there's 1 left over, correct? Do you see what I mean? You with me?
So would the remainder be
So
2?
I'm gonna be at this stage, it's gonna end in a 3. And can you do that? What's your calculator say for 3 to the 21st? I don't know if that's gonna be too big yet or not. It might be. It's too big?
It's
Alright, yep, you have to trust me. Every 4 it repeats. So when I divide by 4, I just see where am I partway through that pattern. If it goes in evenly, I'm at one of the 1s. If I have remainder 1, I'm at a 3. If it has remainder 2, I'm at a 9. If it has remainder 3, I'm at a 7.
3 left over.
No?
What section?
1, 2. Yeah, something to look forward to. So there's a couple problems like this. Guys, all right, 3 to the 11th power. What's the remainder if I divide 11 by 4? 3. The quick way to do that is, what number below 11 does 4 go into? 8. 11's 3 more, that's the remainder. So I'm 3 steps through the pattern, it should end in a 7. Can your calculator do 3 to the 11th? Should be able to. What is it?
177,147.
It ends in a 7, yeah. That's all you gotta do, because it's repetitive. if I divide by 4, I kind of see where I am in the process. If it goes in evenly, I've gone all the way through and I'm back at 1. If it has a remainder 1, I'm one step past that. Yes?
So would the answer be 7? 7's in the ones place?
Yeah, for 3 to the 99?
Yeah.
Yeah, since 4 goes into 99 with the remainder of 3,
Okay.
then I'm at the third step, 7 at the end. Yeah. Now, I think if you type it into Google, it might actually show you. I don't know. Every computational thing has a maximum amount of digits it can handle. So, okay. Letting that problem go for now. Okay. That's just one type of problem. They're not gonna all be that. What about this one? This is related to a urban legend in mathematics. You couldn't really make it a very exciting movie out of this, but the urban legend is Gauss. Have you guys ever heard of Gauss? Friedrich Gauss. He did a lot of shit. He did too much. He should have left some stuff for other people, but he discovered way too many things about mathematics. Have any of you guys, see now, this is gonna go over your head. Back in the day when we had those big ass TVs,
Oh yeah. Big
I had a
boxes.
bunch in the back, right? So sometimes you have to use what's called a degausser.
Yeah.
Because we had a magnet, so I remember being a little kid, I got a magnet, I put it next to the TV, and there was like a little discolored, distorted part of the TV.
Do that on sheet.
My mom was like, what? You know, so we had to get this degausser, and that's what it does. Because Gauss did a lot of work with magnetic fields, so we actually call the strength of a magnetic field, we give it the unit Gauss. I mean, that is the ultimate. If you're a math person and they name a unit after yours,
The Navy uses a lot of
You're
anti-gaussing
big.
and stuff like that.
What's up?
The Navy uses a lot.
There you go.
Anti-gaussing on ships and stuff.
There you go, yeah. Degaussing on the ships is huge, because that'll affect all the instruments, yeah. Guess semi with me, even if you've never heard of it, because that's back in the day with, you know, we had the 8-track tapes with the cathode ray TV tubes, right? Some of you guys might be with me on this. Had to get up to change the channel, it's crazy. So those were crazy kids, we didn't have them streaming, alright, sorry.
That wasn't that long ago.
It really wasn't, it really wasn't, I just like to, I'm old, I like to make me even older. Way back in the day, kids. Oh yeah, so Gauss, he was in like first grade or whatever, and all the students were going crazy. So the teacher said, yeah, everybody sit down, I want you to add up the first 100 numbers, natural numbers, and don't bug me until you're done. Anybody who talks, we're gonna get sent to the whatever, right? You guys kind of with me? Gauss, so you all with me. The problem is, add up the first 100 counting numbers. Gauss did it supposedly in like 10 seconds. And the teacher's like, no, you're wrong. You must. So he said, then the teacher sat down and did it, right? So all the other students like, he's doing this. You guys coming with me so far? So can you imagine if you're trying to add the first 100 freaking numbers? Are y'all with me? How the hell could somebody do that in 10 seconds? And he didn't do it before. He wasn't like at home, and back in his day, they had a candle, and they didn't have TV, so yeah, just playing around with numbers was like a great time. But no, he didn't do it beforehand. He came up with it on the spot. If you just do 1 plus 2 is 3 plus 3 is 6 plus 4 is 10, that's gonna take a long ass time. Y'all agree with me? So the pattern Gauss noticed, what is 1 plus 100? 101. What is 2 plus 99? 101. What is 3 plus 98? 101. So every pair of extremes as you go in is 101. How many pairs would I have? 50 pairs, correct? So I have 100 total numbers, right? Divided by 2 tells me how many pairs I've got. Yes? And then if I multiply, and then if I do 1 plus 100, the lowest number plus the highest number, that is the sum that gets repeated this many times, yes? And what is really, really cool, and I know when I use the word cool, you guys don't agree with me, but this is 50 times 101. What is 50 times 101?
5,050.
Freaking 50-50, are you kidding me? So if somebody says, what's 1 plus all the way up to 100, you go 50-50. Because that's what it is. It's kind of, all right, I won't say cool. It's kind of interesting, maybe, yes?
Yeah.
I need you to understand, he didn't apply a process he'd been told. He came up with that shit. And there's a lot of shit yet to be discovered about our own number system. Do you understand? So this is what math is just playing around, yeah.
So this is just a arithmetic sequence?
So again?
Arithmetic sequence?
Oh, there you go, arithmetic sequence. Yes, I should have asked, I don't know if anybody knew. There's arithmetic sequences and there's geometric sequences. Arithmetic is based on addition. Do you all agree with me that to get to the next number, add 1? So that's an arithmetic sequence. So any arithmetic sequence, I can add up the consecutive numbers in this pattern. I can use this result. Pretty powerful shit, right? We don't know if it's true. It's just an urban legend, like you said. Right? Not as exciting as some of the ones involving cutting things out of people and so forth. Right? Okay. All right. So that's another example of finding a pattern. So then the last couple of things would be make a list.
Oh, that's boring.
Huh? What'd you say?
That's boring.
Yeah, that's funny you say that, because I was about to say, after all that, this is gonna be boring. Some of you guys are like, the whole thing's boring, Jeff. All right, whatever. Oh, okay, that's right. So for example, so now make a list is the next kind of approach. So if I said 2 numbers multiply to be 25, I'm sorry, let's say they multiply to be 25 and they add to be, let's try this again. They multiply to be 136 and they add to be 25. There we go. You see why making a list would be a good option here? There's 2 kinds of lists you could make.
We had a problem like this on Tuesday.
Hmm?
We had a problem like this on Tuesday.
Neato. I don't remember. So you need 2 numbers, correct? And they need to do 2 things. So here's the way you do it. Make a list of numbers that satisfies one condition and then check each one to see if it satisfies the other one. Now, you could be kind of smart about this as you go through. So if somebody give me, it depends. Let's do add to 25 because that's easier to make a list, correct? Things that add to 25. Can somebody give me 2 numbers that add to be 25?
20 plus 5?
20 and 5? And somebody said 21 and 4, right?
She said 12 and 13.
12 and 13? Okay. So if I check, you all agree those all add up to be 25. So I've started my little list. So they match one condition. Do they also match the other one? What is 12 times 13?
156.
156? Yeah, so that doesn't work, right? What's 20 times 5? 100. What's 21 times 4? 84, okay. So you see how these actually got further away? Do you see how that's pretty close? So now I'm gonna stick around there. So as you make your list, you can kind of like refine your next guess. This is a little bit like guess and check, but it's a kind of like, it's making a list in order to do that, right? So then around 12 and 13, what else would you try? 14 and 11. Now here's another thing. What number is that supposed to end in? 6. And this is gonna end in 4, right? Do you see what I'm saying?
Because you can see it from the 21 and 4.
Well, that's supposed to end in 6. This is gonna end in 4. What is 14 times 11?
154.
Yeah. You guys with me? Didn't I get a little closer? Aren't I a little closer to the answer, right? All right, now think about it. 15 and 10, but that's not gonna end in a 6. 16 and 9, that's not gonna end in 6. 17 and 8. What about 17 times 8?
136.
Yay. Okay.
And that's the only possibility?
Yeah.
Besides switching the numbers?
True. Yeah, that is it. Yeah. I don't know if you guys remember, now listen to me. We are not gonna do any of what I'm about to say. You guys remember factoring?
No. Never speak again.
factoring, sorry, you had to do something like this to factor like x squared plus 7x plus 12. Find numbers that add to be 12, add to be 7 multiplied by 12. So this is kind of like just a number puzzle by itself. Okay. Very sorry to dredge up past traumas. And then there's one of my favorite approaches. It's called solve a simpler problem. That sounds very encouraging, right? Given some problem, solve something simpler. That doesn't solve the problem, but it helps you get a feel for what the hell the problem's trying to ask you. I use this all the time in algebra to try to get a word problem started. So, for example, actually, let me do something a little bit more basic. What if I was traveling? I am traveling at 1,587,000. What do you got, Jeff? Miles per day.
What?
And I want to know how long would it take me to go 4,371,962 miles. Alright, so the worst part of this problem is how freaking big the numbers are. Our brain cannot latch onto them. Do you agree with me? You look at those numbers and you're like, no, thank you though, right? Alright.
I think
Yeah, what's up?
are you asking to solve it?
Yeah, sure.
I was thinking maybe multiply that by 4 and then subtract,
Oh.
because it wants us to go,
Alright, wait. Okay. Let's replace those numbers. I'm not gonna change the problem. I'm gonna do a little side work. I'm just gonna replace those numbers with some nice round frickin' numbers. And then I'm gonna see what my brain does. I'm gonna try to give my brain a problem to latch onto, and then I'll just do the same shit with the weird ass numbers. So let's say I'm going 10 miles per day. And it wants me to, how long until I go 20 miles? Do you see how it's the same exact problem, different numbers? You agree? I just gave myself much nicer numbers. So you see how that's a simpler problem? You guys agree? Can anyone see what I need to do? I'm going 10 miles per day. How long until I go 20 miles? 2 days. What did you do with 20 and 10? How'd you get 2? Divided, right? So you divide. So your brain latched on to this problem when you replace the numbers. Does it matter if I would have put a 30 here? Would you have done a different operation? Of course not. So it doesn't matter that these are these. So how do I figure this problem out? I take this number divided by that number, right? So in your calculator, you can put 4,3,7,1,9,6,2 divided by 1,5,8,7. You don't have to sound like that, okay? I love doing that shit. Because the math doesn't give a shit what the numbers are. We do, right? They kind of like trip us up. It should be like 2 point something.
2.7548.
Okay. 2.7548, blah, blah, blah. Days, right? And that many days. Okay. I don't know if you guys are with me or not, but in life, if you have these weird ass numbers and you're trying to figure, you just replace them for a minute with nice whole numbers. And your brain can latch onto that and you go, oh, that's the operation. Let me do the same operation with the freaky numbers.
Like, on average, how many decimal points do you like us to go
Oh, most problems I'll tell you.
to? Okay.
Right? Especially when we get to like the decimal section. But if I don't, a couple places normally is good.
Yeah.
On word problems on, I'll tell you how much to round. Yeah. Okay.
did you mean by like how far past the decimal you would go?
Yeah.
Yeah,
on
where to
average, it's
round.
like 4 to 5.
Yeah. Obviously, if the word problem is about money, you get around to a couple places.
Yeah.
Make it money. If it's distance, a couple places is way more than you normally do. If I said how far away you live and you said 11.58 miles, I'm gonna look at you a little funny.
11 and a half.
Kind of with me? You would say 11 and a half at most, and not 11.58. Like, who are you? Okay. Just Google that shit. Because Bing didn't tell me the right thing. Okay. You guys kind of, all right. Okay, so, let me do this. Let me give you this. We'll do some of this. And then we're gonna head out a little early. Oh, actually, still gotta do all that. But I do wanna show you, some videos of little people that might eventually be like your students. So, I kinda promise you, I finally remembered my password to get in this thing.
Quick, what was it?
Yeah.
Hey, worth a shot.
So let's take a random number. What's your credit card number? Let's just pick a random number. So, alright, we're gonna see some, students show up more and more. You're gonna get some favorites.
Oh, it's the same children each time?
For the most part, there are some, I don't know how these lights really work, oh, screw it, they're just all gonna go away. All of them? Yes, okay, that's fine. Nothing else. Let's not flash your ears, let's see how this is.
So I'm placing some cups out here, and what I would like you to do is I would like you to go over there on that chair and get exactly the right number of straws, so there's exactly one straw in every cup. Then you can go ahead and put them in the cups. All right.
Alright, real quick, okay, so, what was she doing? She did it correctly. What was she doing? I gotta not record, cause they'll copyright